All right, today we've got a story for you that sounds like it's straight out of science fiction. We're talking about a showdown between the absolute giants of quantum computing and a really unlikely challenger that might just flip the script on how we think about the future of processing power.
So let's just get right to the heart of it. Here's the big question we're tackling today. Can a network of, yes, gaming GPUs, the same kind of hardware that powers your favorite video games, actually go head-to-head with a multi-million-dollar, super-cooled, lab-grade quantum computer? The answer? Well, it's not what you'd expect.
And the challenger's name? It's a decentralized network called Qubitcoin. And believe it or not, it's putting up a serious fight. So for the next few minutes, let's unpack exactly how this is even possible.
So what is Qubitcoin really? Well, at its core, it's this massive distributed computer. We're talking about roughly 2,000 high-end GPUs, all linked together from around the world, creating one seriously powerful network. And this is the key, they're not just mining crypto, they're performing tasks that actually simulate quantum behavior.
But this, right here, brings us to a huge problem. How in the world do you fairly compare a classical, distributed network with a true quantum processor? They work on completely different principles. A GPU is a beast at crunching numbers one after the other, super fast. A quantum computer, though, it uses the sheer weirdness of quantum mechanics to explore tons of possibilities all at once. It's the definition of an apples and oranges comparison.
So to solve this apples and oranges thing, we need a universal yardstick, and that's where the Q-tier system comes in. Honestly, the best way to think about it is like horsepower for a car. It doesn't matter if it's a V8, an electric motor, or a hybrid. Horsepower gives you one number to compare them. Q-tiers do the exact same thing, but for quantum calculations. It's all about effective quantum throughput.
And here's how that whole system lays out the landscape. Down at the bottom, Q0, that's our everyday classical hardware, like GPUs. But as you start to climb the ladder, Q1 and Q2, you get into the territory of today's top quantum computers from giants like Google and IBM. The higher tiers, Q3 through Q5, well, that's where we're headed in the future. So this is the scale we're going to be using.
Okay, so before we can actually place Qubitcoin on that scale, we need to know what we're up against. Let's meet the heavyweights, the state-of-the-art quantum processors that are setting the gold standard for 2025.
Here are the big names on the block: Google's Willow, IBM's Heron and Nighthawk, and IonQ's Tempo. And you can see they use different approaches. Some use superconducting circuits, others use what are called trapped ions, which are pretty much what they sound like, tiny charged particles held in place with magnetic fields. But, as we're about to see, the number of qubits isn't the whole story.
So here's the thing, and this is absolutely crucial. Just having more qubits doesn't automatically make you better. The real measure of power, the number that truly lets us compare these different machines, is throughput. How many meaningful quantum operations can that machine actually pull off every single second? That's the key. And just look at these numbers. IBM's Heron processor, for example, can perform around 12.5 million quantum operations per second. Google's Willow is right there behind it. This is the top-tier performance we're talking about for dedicated quantum hardware in 2025, and this really sets our benchmark for what a Q2 machine looks like.
All right, the stage is set. We have our universal yardstick, the Q-tiers. We know the power of the reigning champs. So it's time for the verdict. Let's see where the Qubitcoin network officially lands in all of this.
This is the moment of truth. Where does our distributed network of gaming GPUs really fit into this quantum hierarchy? And the results? Well, they're pretty mind-blowing. When you measure it by those equivalent operations per second, the Qubitcoin network has a throughput that is 3 to 4 times greater than an IBM Heron quantum computer. Yeah, you heard that right. A distributed network is outperforming a leading quantum machine by a pretty huge margin.
So what does that actually mean on our Q-tier scale? It means Qubitcoin gets an official classification of Q2 lean. This puts it firmly, without a doubt, in the same performance tier as the dedicated, multi-million-dollar processors from IBM and Google. This isn't a hypothetical challenger, it's a legitimate competitor playing in the big leagues.
So, the question on everyone's mind has to be, how? How is this even possible? This isn't just a story about brute forcing a problem with more hardware. The answer lies in the network's incredibly clever and efficient design.
Here is the secret sauce. First up, you've got this feature they call Bring Your Own Solver. It basically lets users run highly specialized code that is perfectly optimized for their specific GPU, squeezing out every last drop of performance. Second, there's a system called Proof of Progress, which rewards people for doing meaningful computation, for actually solving problems, not just pointless hashing. This combination allows the network to effectively simulate a really powerful quantum system, landing it right in that Q2 sweet spot.
Okay, so this is really cool tech for sure, but this is way more than just a tech demo. The results here have some massive implications for the entire future of high-performance computing. So let's zoom out and take a look at the big picture.
And really, when you boil it all down, the takeaway is powerful. What this is showing us is that the future of incredible computing power might not belong only to single, centralized, monolithic machines built in a lab. It could very well belong to powerful, efficient, decentralized networks that harness the collective power of hardware from all over the globe.
And that leaves us with this massive, final question to chew on. As we keep pushing the boundaries of what's computationally possible, is the next great leap going to come from one single perfect machine? Or will it come from the coordinated effort of millions of devices, all working together? This showdown suggests that race is far, far from over.